Welcome to the presentation of our online course, Introduction to Enzymatic Bioconversions Technology and Engineering. Through our online courses series, you learn the principles of bioprocess engineering and their applications to enzymatic bioconversions, microbial fermentations, and animal cell cultures processes. For more details, visit us at bioprocessengineeringonline.com. Enzymes are proteins that catalyze biochemical reactions in living cells. Thanks to their remarkable biocatalytic efficiency and specificity, enzymes are being increasingly used across various industries, including food, chemical, pharmaceutical, cosmetic, and biofuel sectors. The most interesting industrial properties of enzymes are their wide range of catalytic activities in both aqueous and non-aqueous media, their ability to operate under mild conditions of temperature, pressure, and pH, their high levels of chemo, regio, and enantio selectivity. These features make enzymes valuable tools for producing novel molecular architectures that are difficult or impossible to achieve through conventional chemical synthesis, for developing more efficient and sustainable production processes with fewer reaction steps and reduced reliance on toxic or hazardous reagents. For bioprocess engineers, a major challenge is the design and scale-up of enzymatic bioreactors that are both efficient and economically viable. This process begins with small-scale laboratory reactors and progresses toward large-scale systems using either soluble or immobilized enzymes, capable of producing products at the kilogram to ton scale. This introductory course in enzymatic bioconversion technology and engineering is intended for students and professionals who are new to bioprocess engineering and/or its applications to enzymatic bioconversions. Participants will first become acquainted with the enzymatic bioconversion technologies, commonly used in industry. The course also provides a foundational understanding of how bioprocess engineering supports the simulation, scale-up, and optimization of enzymatic reactors for industrial applications. The course is organized into 3 sessions, covering enzymatic bioconversions technology and cost, enzymatic conversion kinetics and simulation, and enzymatic reactors optimal operation. The 3 sessions can be taken independently. Session 1 begins with an overview of industrial bioconversions. It introduces the main classes of enzymes commonly used in industry, including hydrolases, oxidoreductases, isomerases, and transferases. The session also covers key types of bioconversion reactions, such as the synthesis of fine chemicals, active pharmaceutical ingredients, chiral intermediates, bioactive cosmetic compounds, the production of food and beverages, the conversion of renewable resources into biofuels and bio-based chemicals. The session then reviews the types of bioreactors commonly used in industrial applications. It begins with soluble enzyme bioreactors, exploring various configurations such as stirred tank reactors, cascades of stirred tanks, tubular reactors, membrane bioreactors. The session then continues with immobilized enzyme reactor technologies. It covers key enzyme immobilization methods and examines common bioreactor configurations, including stirred tank reactors and fixed bed reactors. Finally, Session 1 introduces the economics of bioconversion processes. It presents the methodology used to evaluate bioconversion costs, focusing on key cost contributors such as equipment, enzymes, and labor. Understanding cost evaluation is essential for optimizing the economic performance of bioconversion processes, especially given the wide variation in enzyme costs, which can range from €100 to over €100,000 per kilogram. The next two sessions introduce the engineering principles of enzymatic bioreactors. Bioprocess engineering is a scientific discipline that offers a conceptual and methodological framework for understanding, simulating, scaling up, and optimizing bioreactors. Its goal is to ensure the most efficient and productive use of enzyme biocatalysts in biomanufacturing processes. Session 2 focuses on the kinetics and simulation of enzymatic bioconversions. It introduces the bioprocess engineering approach used to determine and analyze the kinetic parameters of enzymatic systems. Building on these insights, the session covers the development of knowledge-driven simulation models for bioreactors, enabling a deeper understanding and more effective control of enzymatic processes. Session 2 begins with a review of the kinetics of bioconversions, catalyzed by soluble and immobilized enzymes. It examines how bioconversion rates vary over time during processing. The session also explores the dual effect of temperature, the most critical operational variable. While increasing temperature typically enhances the intrinsic reaction rates, it also accelerates enzyme denaturation, potentially reducing overall process efficiency. The session then highlights the key biochemical and physical phenomena that govern bioreactor kinetics. These include the enzyme catalyzed reaction, the enzyme denaturation process. When enzymes are immobilized on particles, additional factors come into play, such as mass transfer limitations, fluid flow dynamics. Session 2 finally introduces the knowledge-driven methodology used by bioprocess engineers to develop simulation models of bioreactors. This approach integrates mass balance equations with the kinetic laws governing enzyme reaction and denaturation as influenced by temperature. These simulation models serve as digital twins of real bioreactors. They enable efficient virtual experimentation, digital scale-up, and process optimization, greatly reducing the need for costly and time-consuming physical trials. Session 3, Optimal Operation of Bioreactors, introduces the core principles for optimizing bioreactor performance, emphasizing the alignment of operational strategies with the specific kinetic behavior and economic considerations of the bioconversion process. The session specifically addresses key questions such as the choice of bioreactor technology, batch versus continuous operation, in the use of soluble versus immobilized enzymes, the determination of the optimal operating temperature, balancing reaction efficiency with enzyme stability. Compared to simple batch operation, continuous processing offers key advantages, including reduced downtimes and consistent, steady-state production. Through bioreactor simulations, the session illustrates how enzyme cost critically influences the choice between batch and continuous operation. You will also explore how the kinetic properties of the enzyme affect the selection of the most appropriate continuous reactor configuration, whether it be a stirred tank, a cascade of stirred tanks, or a tubular reactor. The session also focuses on the choice between soluble and immobilized enzyme reactor technology. It highlights the advantages of immobilized enzyme systems, particularly when immobilization leads to a significant increase in enzyme stability, a key benefit in bioconversions carried out in organic solvents. You will also examine the crucial role of enzyme cost in determining whether a soluble or immobilized enzyme reactor is the most suitable option for a given process. Finally, the session addresses the critical question of determining the optimal operating temperature for an enzyme bioreactor. For industrial enzymes, operating temperatures can vary widely, from 10 degrees Celsius to 100 degrees Celsius, depending on the enzyme's characteristics and the bioreactor operation mode. Using bioconversion simulations, you will explore how enzyme stability and enzyme cost play key roles in defining the optimal bioreactor temperature. The course resources include recorded slideshow presentations covering enzyme kinetics, bioprocess simulation models, bioprocess economic evaluation, bioreactors operation and optimization. In the 3 sessions, you will use spreadsheet templates to analyze bioconversions kinetics, simulate bioconversions in their batch and continuous modes, evaluate bioconversion cost, and optimize bioreactors operation for minimal production cost. You have the flexibility to tailor this online course to your individual pace. Plan and structure the course according to your own schedule. Additionally, coordinate the interactions with your tutor through video meetings. For further information on the course, please visit our Bioprocess Engineering online website or contact us at bioprocessdigital.com.